The Java volatile keyword is a special keyword which can be applied when declaring a variable. As you can see in the example here on the left, I have declared the second variable volatile by adding the volatile keyword here to the variable declaration. By declaring a variable volatile, you tell the Java virtual machine that this variable must always be read directly from main memory. And when the variable is changed, the changed value must be written directly back to memory immediately. If a variable is not declared volatile, we have no guarantee about how often the variable will be read from main memory here up into a CPU register, and how often when the value is changed up here, the variable is changed up here in the CPU register, that this value is written back to main memory. This will happen from time to time, but there's no guarantee about when it happens. So if you imagine for a second here that neither of these two variables were declared volatile, so both of them are not declared volatile, then what could happen is you have thread 1 calling set object here. It sets two new values for object and has new object. But the Java virtual machine decides to keep these values only in the CPU registers here and not pushing them back to main memory. So when thread 2 here calls get object down here and it tries to look at has new object, well, then it sees, maybe it sees the old value which is stored in main memory, or maybe it sees an old cached value of has new object, which it has stored in its own registers from last time it called get object. So, and the same is then true down here with the object variable. It might see an old version read from main memory, or it may have an old cached version over here. So as you can see, if we do not declare any of these two variables volatile, then we will have some visibility problems, and the Java volatile keyword helps with these visibility problems by providing a visibility guarantee, which I will explain shortly. The Java volatile keyword visibility guarantee is as follows. Whenever you write to a volatile variable, then that variable and all other variables that are visible to that thread will be written directly back to main memory. As you can see here, the has new object is declared volatile, but the object variable is not declared volatile. So in the case here, when thread 1 calls set object, then at the time we set a new value for object, well, object is not volatile, so we are not forced to write anything back to main memory yet. But when we set has new object to true, then because you can see here that has new object is volatile, we are forced to write that value back to main memory and all other values that are visible to the thread at that time. Now, when I say we are forced to write it back, it is the Java virtual machine that is forced to write it back, and it happens behind our back. So this is not something that we are actively engaged in. It just happens. Similarly, whenever a thread reads a volatile variable, then the value of that volatile variable has to be read directly from main memory. Additionally, any variables that are visible to the thread at the time it reads the volatile variable also has to be refreshed from main memory. So in the example up here, when thread 2 calls get object and it iterates through this loop, and for every iteration it reads this volatile variable here, has new object, which is declared volatile, then the value of has new object has to be reread from main memory. Additionally, because object up here is also visible to thread 2, then the value of object also has to be reread from main memory for every iteration in this while loop. So as soon as thread 1 changes the value of has object, has new object here, then the value of has new object and object will be pushed to main memory and will thus become visible to thread 2. And then thread 2 will exit this loop and will read the correct value of the listed object variable, because the listed object will also be refreshed from main memory. And then thread 2 will set has new object to false, which will again cause has new object to be flushed back to main memory here. And of course the rule is the same, that all other variables that are visible to thread 2 will also be flushed back to main memory at this time. The Java compiler and the Java virtual machine are allowed to reorder instructions in your application as long as the reordering does not change the semantic meaning of the application. Unfortunately, instruction reordering may break the Java volatile visibility guarantee, causing your application to malfunction in a multi-threaded situation. Let me explain via this diagram here created for that purpose. We have created here a new class called exchanger2. It has 3 variables here, of which only one of them is declared volatile. Now imagine you have thread 1 calling set values here, and so from this values object here it will obtain value 1 and value 2, set it to assign the values to val1 and val2 up here, which are not volatile, so nothing will get written back to main memory just yet. Then val3 from the source object here will be assigned to val3, and because val3 here is volatile, then we have all the variables here, all the values here being pushed to main memory at this point in time. Similarly, you can see here in get values, when thread 2 calls get values, we start by reading val3 and from this val3, right? And because val3 is volatile, that means that at this point in time here, both val3, 2 and 1, all of them are read in from main memory. And so that means that in whatever CPU registers are stored here, then that means that we have now the freshest values here stored in the CPU registers, right? So val3 is written then into the destination values object here, and these 2 other just recently refreshed values will be written into val1 and val2 of the destination values object as well. Now this worked just fine as long as the sequence of these instructions are not changed. Right, for this to work, over here, setting or reading val3 must be the last thing that happens here, or setting val3 here must be the last thing that happens here, so that we push all these 3 freshly changed values to the main memory. And over here, the reading of val3 must be the first thing that happens here, over here, so that we refresh all of these values, val3, 1 and 2, directly from main memory at this point in time before setting them into the values object. Now imagine what happens if the Java virtual machine or the compiler decided to say, hey, it doesn't really matter in which sequence these instructions here are executed, right? In the end, all that happens is that val3, val1 and val2 are set into this destination object. So why could I not change the sequence here? Or over here, oh, it doesn't really matter in which sequence we read the values out of the values source object here and write them into val1, val2 and val3, and decided to reorder the instructions. Then obviously the time at which the values are forced written back to main memory and forced read from main memory will change. To illustrate the problems that instruction reordering may cause, look at this modified version of the exchanger2 class, and imagine that instead of having val1 here assigned as the first instruction up here, it has been reordered so that it is now executed as the last instruction over here in set values. Now notice what happens is that first we set the value of val2, which does not cause any synchronization to main memory. Then we read the value of val3 here from the source object and set val3. And because val3 is volatile, then at this point both val1, val2, and val3 are forced synchronized back to main memory because all three variables are visible to thread 1. However, we have not yet set the new value for val1, so the value for val1 that is flushed back to main memory is an old value. Now you can see here that the instruction reordering of moving the assignment of val1 down here after val3 causes a Java volatile visibility problem. We are breaking the visibility guarantee of writes. Similarly, imagine that instead of val3 here being read as the first value read inside of getValues here, it is now reordered to be the second variable that is read. Now, because of that, that means that whatever value is stored in the val1 variable at this point in time here is what will be written into val1 of the destination object. And we don't know what that value is. It's probably the one that is stored from the last time setValues was called, or getValues was called actually. And then when we read val3 here, because that is a volatile variable, then all of val1, val2, and val3 are refreshed in from main memory at this point in time. So a new value will be read for val1, val2, val3, but val1 has already been set here into val1 of the destination object. And so the new value that is just read in here is ignored. In fact, it will probably be set the next time that getValues is called, but then it's not matching the other two values which were set in the previous call to setValues. So as you can see, instruction reordering on the reading side here has also broken the visibility guarantee of the Java volatile keyword. So instead of reading val3 first, we now read val1 first, causing the visibility over here to be to malfunction in a multi-threaded setting. To avoid instruction reordering breaking the visibility guarantee of the Java volatile keyword, the Java volatile keyword also comes with a happens before guarantee. And the happens before guarantee is thus: all writes to volatile or non-volatile variables that happen before a write to a volatile variable will remain before the write to that volatile variable. So over here in this example here in the setValues method, the write to val3 here, which is volatile, means that the two writes here will have to remain before this write to val3, so they cannot be reordered to happen after the write to val3. Now these two instructions here can be reordered among themselves, so you can set val2 before val1. That doesn't matter. This reordering is allowed, but neither of them can be reordered to happen after the write to val3. So all writes that happen before a write to a volatile variable will have to remain before the write to the volatile variable. Similarly, all reads of a volatile variable that happens before reads of other non-volatile or volatile variables will have to remain before subsequent reads of volatile or non-volatile variables. So in this situation here in getValues, that means that this read of a volatile value here of a volatile variable val3 will have to remain before the reads of val1 and val2. And so that means that the reading of val1 and val2 can be reordered among themselves, but neither of these two instructions can be reordered to happen before the read of val3. Right? So the reading of the volatile variable will remain before any subsequent reads of volatile or non-volatile variables. Obviously, this direct reading of volatile variables from memory and writing of variables directly back to memory after updating them causes a small performance penalty. So you should only use volatile variables when you actually need the visibility guarantees provided by volatile variables. If you do not need that, if you are writing some code in a single threaded context, you should not use the volatile keyword. So you should think about it. It's not going to completely ruin the performance of your application, but it will slow it down. So if your application is performance sensitive, there's no reason to use the volatile keyword except in the cases where you actually need visibility of data between threads. You should keep in mind that using a volatile variable is not always enough, and I will illustrate why using this example here. Look at this counter. Imagine that we have a single counter instance and we have two different threads, or maybe more, calling the inc method concurrently. Now you can see that the count variable up here is declared volatile, so we will always read the value of the count variable directly from memory, and we will also always write the value directly back to main memory when updated. Now imagine if the count is 9 and we have two threads entering here inc at the exact same time. Both of them will execute this if statement. They will see that count is not equal to 10. Both of them will see that because count was 9, right? And so both of the threads will progress beyond the if statement here, and both of the threads will execute the count ++ instruction here, the incrementation of count. Now, first of all, if this was supposed to be a concurrent counter, the fact that the counter is designed to stop at the value of 10 and it still allowed two threads or even potentially more threads to progress beyond this point is clearly a mistake. This is a case where it is not enough that the count variable is volatile. This whole block here should have been declared synchronized as well. So that is one problem, right? So the second problem is that the incrementation instruction in Java is actually not atomic. So the increment instruction consists of a read of the variable, right? So first the variable is read in from main memory. We have an increment of the variable, which happens in a local register in the CPU, and then we have a write of variable directly back to memory. Now, in the case where two threads have progressed beyond this point, well then both of them will read the value 9 for the value of count, and it's read into a register. Then in that register, both of the threads will increment the count variable, but they will increment their own copy. And both of the threads just read 9, so both of them will increment the count variable to 10. And then both of the threads will write their value back to main memory. Now, clearly, if this had to function correctly, then the total count value should have been 11, right? You have two threads adding 1 to a counter that is 9. That should result in first the variable becoming 10 and then 11 and then written back to main memory. However, both of the threads will write the value 10 back because they read the value of count at the exact same time. Now, obviously, if the threads were just a little bit delayed so that one thread would read the variable, increment the variable, and then write the variable back, then the two variable or the second thread would then obviously read the variable value written by the previous thread and then update and increment and write back correctly. However, this is not a guarantee that we have here. This is also possible in the instance that the count variable is 0, right? Both two threads pass beyond the if statement because the count is 0. Then both of them read the value 0, add 1 to it, and write the value back. So both of them write the value 1 back to main memory. And so, as you can see, that is probably not what was intended with this counter here. So instead, you should use a synchronized block or make the whole method synchronized. Or you could use an atomic integer as count variable instead, or one of the many atomic, like an atomic long or some of the other atomic utility classes in the Java util.concurrent package. So just keep that in mind. Using a volatile variable is not enough always to guarantee correct concurrent behavior. Sometimes you need more. That is all for this video about the Java volatile keyword and the Java volatile visibility guarantee and Java volatile happens before guarantee. Remember to check out the description below the video for a link to a textual version of this tutorial, as well as links to other related tutorials. If you like this video, hit the like button, and if you want to see more videos like this, subscribe to my channel.